Next, we're going to look at a related decomposition to the polar decomposition, and it is the singular value decomposition. This basically involves, instead of breaking down T into what it does in terms of eigenvectors and eigenvalues, we're actually going to look at just the eigenvalues and eigenvectors of the positive part, roughly speaking. So the way it goes is as follows. So the singular values of an operator are the eigenvalues of its modulus, or the square root of T star T here. And they come with multiplicity equal to the dimension of the eigenspace of that operator. And the singular values of T are going to be non-negative because, as we noted before, the root of T star T is a positive operator. Okay, so let's look at an example. And this is example 750 in the book. If we define an operator on F4 as follows. So let's take T of NR, let's see, so we've got Z1, Z2, Z3, Z4, and we will define it to map this to 0, 3Z1, 2Z2, and minus 3Z4. So pretty simple operator here, not a whole lot going on. And that's because we don't want to make a complete mess out of the example. It often turns out that the singular values are somewhat complicated, and they typically involve square roots based on the way that they're defined. So good for numerical stuff when the computer can think of it, but a bit of a chore on pencil and paper. So let's look at the matrix of T now. So the matrix of this transformation is, in the standard basis, it's going to have zeros in the first couple of slots on the diagonal, and 3 and 2 under the diagonal, and a minus 3 here. Okay, and it's going to be 0 everywhere else in the matrix. So all the entries that I didn't write are also zeros. Then the matrix of the adjoint is going to be the conjugate transpose of this guy. So it's also almost a diagonal matrix, except now we have the 3 and the 2 just above the diagonal, like so. And if we look at what the adjoint does to some point, let's actually call them W's, W1, W2, W3, W4, then this is going to give us 3W2, 2W3, 0, minus 3W4. Okay. So then when we compose these guys on some unsuspecting Z, we're going to get 9Z1, 4Z2, 0, 9Z4. And if we do the square root then, we get 3Z1, 2Z2, 0, 3Z4. So what do we get from that? Let's see. We've got square root of T star T applied to our first standard unit basis vector. Gives us 3 as an eigenvalue. And if we apply it to the second unit basis vector, we get 2 as an eigenvalue. And on the third unit basis vector, we get 0. And last but not least, on the fourth, oh, I just realized I typoed in the line above. I was thinking too much about zeros. There we go. And then for this one, we've got 3. All right. So the spectrum of square root t star t is 3, 3, 2, 0. And the singular values of t are exactly these guys. Okay, and so it's interesting to notice something here, and that is that 0 and -3 are the only eigenvectors of t, and these correspond to the eigenvectors 0, 0, 1, 0 and 0, 0, 0, 1. And so you can check if you like. If you look for the eigen values and eigenvectors of t, that's all you'll find. But since t star t is positive, and self-adjoint, it will have as many eigenvalues as the dimension of the space that we're working with. Speaking of which, I don't know if I mentioned this earlier, but everything in chapter 7 is finite dimensional. There's a warning to that effect on the first page of chapter 7, but it's very hidden. I challenge you to find it. Yeah. Okay, so that's it for this example. Next, we'll look at the actual singular value decomposition.